Welcome back, friends. Today we shall try some more problems pertaining to our career-oriented course in mathematical modeling using Maple, and we shall try to more effectively use Maple components to deal with the physics part that is planned. Here we have loaded the Maple software. Now we shall consider a function for a plot, and we shall find the derivative of the function. We shall find second order derivative of the function, and this is a very precisely selected function. The function goes as f, we assign x cube plus 4x square plus 2x minus 1. Now, we shall try to plot the function, its first order derivative, its second order derivative, and we shall understand the way we learn in calculus that a function, if possesses maxima, its first order derivative vanishes. Even at minima, first order derivative vanishes. However, at local maxima, the second order derivative is negative, and for minima, second order derivative is positive. That we already know. We shall run this test quickly to find out the things. The first order derivative 3x square plus 8x plus 2 equal to 0. This condition will offer us two roots which are appearing as equation number 4, and these two roots, if you want numerical value of that, you can use eval function to work out that, and it appears that minus 0.27 and minus 2.38, these are the two locations on x-axis where the function possesses either maxima or minima. Now we want to confirm which is maxima or which is minima, or both are maxima or both are minima. To test that, we shall find second order derivative of the function, and the second order derivative of that function obviously is 6x plus 8. Now the test goes as, if the point is substituted for 6x plus 8 equal to 0, we shall substitute the value of x which we have just found into 6x plus 8. Now that if the answer is positive, then the function has minima, and if the answer is negative, the function has maxima. So substituting these values minus 0.27 and minus 2.38, we get first value positive. If the result is positive, it means that the function has minima, and if the result is negative, it means it has a maximum. So here it clearly appears in the equation number 7 that the first point pertains to minima and second point to maximum. Now we can plot this function, same function I have picked up with another variable y, so that it should not mix with the earlier one, and we can plot the function. Now you can clearly see that function has a minima and a maxima, and that is in the zone minus 4 to plus 1. So for exploring this kind of thing, one has to priorly know the region in which the function has minima or maxima. Now the first derivative we shall plot along with this. Here you can clearly see that the point, the blue graph shows maxima here, and the point where it has maxima, at that point the first derivative function has 0 value, whereas the another point of the blue curve has a minima at this point, and at this point the first derivative curve again intersects with x-axis. Now, here we are plotting function g, its first derivative and its second derivative in the same region. So the green line indicates function which has a maxima and a minima. The blue line indicates first derivative which shows zero value at the maxima and again a zero value at minima. The second order derivative is the line which shows negative value for the point where we have maxima, and the point where function has minima, the straight line is having positive value. So here we have visually seen how a function and its first order derivative and second order derivative can help us visually supported backup. Friends, now we shall solve a second order differential equation, which is a simple one, and while studying physics we often encounter with that, and the equation is m into second order derivative of displacement with time is equal to minus k times x. Obviously x is function of time. So this is the differential equation which governs the motion of simple pendulum, you can say, or in general you can call simple harmonic motion. So here there is no dissipative factor, therefore this equation is very simple, and here we are using a command dsolve. Dsolve means it's solving differential equation. Inside parenthesis we have this differential equation, and this is to be solved for x of t, that is placed here. So the moment you press enter key here, it offers you solution. C1 and C2 are the constants appearing in equation number 1, and under root k by m is omega in general while we deal that equation theoretically on the blackboard. Now we can solve the same differential equation for boundary conditions, and now along with dsolve we are using x of 0, that is when t is equal to 0. So x of 0 is 0.01 and first order derivative of the same is 0.3. So these are the boundary conditions, and the moment you press enter key you get a solution like this, and it can be plotted. So this is the plot. Now here I have made a little change. In the numerical oriented differential equation, I have plugged in 100 grams or 100 kg you consider in SI system, mass of the object, and the spring constant here is 4900. So this is the second order differential equation of undamped motion, and the initial value x of 0 is equal to 0, and the first order derivative indicates equal to 1. The solution generated is this, and the plot looks like this. Now if we begin the starting point, that x of 0 at 0 time, it is at the full amplitude, and again its derivative is 1. Let us try to run the program by pressing enter from the beginning. So this generates a solution. So here you can see the solution, that at t equal to 0 the amplitude is 1, and then it goes on rolling accordingly. So here the solution is a linear combination of sine function and cosine function. Now friends, we shall try to use the command of animation, and the command of animation we can use to roll a parameter over time or anything like, and you can plot one function, two functions, or many at a time. Now here we have tried to plot a sine of t function where t rolls uh, to describe about 3 cycles, and another sine function where the amplitude in the first sine function the amplitude is 1, in another function sine function is multiplied by e to the power minus t by 5. So a exponentially decaying function is being taken care of, and you can see the animation. So as time rolls, the sinusoidal function of amplitude 1 uh, goes like this, and at the same time the exponentially decaying function appears as shown. Now we shall try to learn the second animation. In the second animation, we have two functions. The first function is a sine function, and second function is sine function plus a phase of pi by 2 is introduced. And again, it is describing 3 cycles. Let us see the animation. So the red line indicates the first function sine of t, whereas the second blue line indicates a function with phase plus pi by 2. Now let us look at the minus pi by 2 phase difference. See how things roll up. So the blue line is with minus pi by 2. So this helps students in understanding the phase difference, which is charted at x-axis. We can plot Lissajous figure using this, but this time animation is a function of is depending on two functions which are parametric in time, and it plots an infinity-like figure that we encounter in Lissajous figures. Now friends, we have equation number 1 which appears on the screen, and this is outcome of application of Wyatt-Sabret's law. N is the number of turns of the coil, mu0 is permeability for free space, current we are having notation current only, rho is the radius of the coil, and x is the distance along axis of the coil where the origin of the coordinate system lies at the center point of the coil. Now here we have preferred some numerical values. That current is 200 milliampere, number of turns are 50, mu for free space we have picked up, and radius of the coil is 5 centimeters. It is converted into meters and shown up here. Now these parameters are keyed in. Now under this we have the new formula given by equation number 3, b equal to. Now we can generate a plot where x is a variable, and the implicit plot command is generated by right clicking this equation, and let's try this. If we right click upon this, we can look for a plot builder or two-dimensional implicit plot where x is on x-axis and b is on y-axis. But here we have one variable rho, that is the radius of the coil, so you cannot get a straight graph. Here we shall have preview, and the implicit plot generates a graph which is to the scale, and as one travels away from the center of the coil, the magnetic field rapidly diminishes. Now I am picking up the function which I want to consider for plot, and this is copied. It can be taken up into plot. I want to make a minor change. I don't want to substitute the value of row. After deleting value of row, we shall press the enter key, and the equation, let us press enter key from the beginning. We start equation 1 quantities. These are substituted here, and here we obtained the equation in terms of row. So here x is a variable on x-axis as one travels away from the axis of the coil, and this quantity can be picked up into the clipboard, and we can use a toolbar to take assistance, plot builder. Then you can press here, add an equation. This is the quantity B which is being plotted on y-axis. We accept this equation. Here we have two variables, rho and x. Okay. Now we want a plot with one interactive parameter. So this is selected. X rolls from -10 to +10, and the value of rho we can prefer from 0 meters to 10 meters. And now we can preview the plot. Now here we have a slider variable where the half value, it has automatically selected, that is 5 meters radius coil. Now as one goes beyond 10 meters distance, the magnetic field diminishes to almost 0. If you change the value of the radius of the coil, I mean as we are decreasing radius of the coil, the magnetic field vanishes quite rapidly as one goes away from the center of the coil. Now friends, we are at a very interesting example where we write a differential equation for LCR circuit, and the differential equation which is written here is raised from the physical situation, and we have selected q of t minus q0 by c as the last term. The special reference to q0 appears there in the discussion. Now this differential equation will look as L into second order derivative of q of t with respect to time plus r first order derivative with respect to t of q of t minus plus q of t minus q0 by c equal to 0. Now the boundary conditions are that at t equal to 0, the charge in the circuit is 0, and obviously current, which is rate of flow of charge, that is also 0. That is the boundary condition. And here that ODE1, that is ordinary differential equation 1, has been solved for BCS1, that is boundary condition 1. So here we obtain this solution. This solution appears little clumsy, but we shall pick up this equation in the clipboard, and we shall carry this forward to plot. Let us select the option plot, tools, then assistant, and then power builder. And then we shall key in expression here as we shall accept this. Now we shall select interactive plot with 4 parameters, and on x-axis we want time, which rules from 0 to 2. The slidable parameter L, we want L to be 0.001 to zero point 0.1 Henry. Resistance we prefer from zero point 0.1 to 2 ohms. Q0 we have selected 0 to 2, so arbitrarily it selects at the middle, that is 1. So amplitude we are considering 1 at the beginning, and C is 0.00001 microfarad. Sorry, it is 10 to the power minus 4 farad to 0.01 farad. Now let us preview this plot. Now if you change L, see in this differential equation we can change the parameters. If we change L, it goes like up to 2 seconds the saturation level is attained, and the fluctuations that are coming up, that depends on L. Similarly, if we change C, we can see a visual effect how the transient current in the circuit will settle. So for this combination, the transient current almost takes 1 second to settle down, and if we choose R equal to 0, we don't have selected that baseline, but as R decreases, uh, the oscillations reside for longer and longer time, and when R will become 0, that we have not opted, but the fluctuations will last for longer and longer time as R increases. As we increase R, the damping decreases and we get this kind of plot. So we can generate such a plot